In Lesson 12.1, we're going to concentrate on functions which are graphed on a specific interval and also something called a removable discontinuity. Some functions are not continuous for all real numbers, or the interval from negative infinity to positive infinity. Some have implied domains, and those are going to be the ones that we've studied previously, those that involve division, even roots, and logarithms, while other functions will have explicitly stated domains. We'll get to those in just a moment. So in example 1, we're going to graph each function and then state its domain using interval notation. What we know about a logarithm is that the argument of a logarithm must be positive. So for this logarithm, the argument x plus 3 has to be greater than 0, which means that x has to be greater than negative 3. So if we give that in interval notation, that's the interval from negative 3 to positive infinity, and that's going to be our domain. In order to graph this function, I'm going to suggest that we set up a table of values. We need to plug in some x values, and in order of operations, add 3, and then take the log base 2 of each of those values. Numbers that we know how to take the log base 2 of easily are 8, and the log base 2 of 8 is 3. 4, the log base 2 of 4 is 2. 2, the log base 2 of 2 is 1. 1, the log base 2 of 1 is 0. And 1/2, the log base 2 of 1/2 is negative 1. That will give us enough of an idea of what this graph looks like. If we have the value for x plus 3, we can find the x value by subtracting 3. And for purposes of graphing, it's easiest to think in mixed numbers. Now we can just graph our x versus y values. And remember, this last column is what y equals. So 5, 3 and 1, 2, negative 1, 1, negative 2, 0, and negative 2.5, negative 1. Now, if we wanted to go a little farther, we can take the log base 2 of 1/4, which is negative 2, and if we subtract 3 from that, we get negative 2 3/4. So we can also graph a point negative 2 3/4, negative 2. What this is going to show us is a graph that looks like this and approaches a vertical asymptote here. So our vertical asymptote I'm going to show with a dashed line because it's a guide to the graph, not actually part of the graph. And that's the line x equals 3. And the graph is the graph of y equals log base 2 of x plus 3. In B, since there are no problem operations, no division, no even roots, no logarithms, the domain is usually all real numbers. However, the domain here is what we call explicitly stated. X cannot be 2. So our domain for this graph is, or for this function, is the interval from negative infinity to 2, union the interval from 2 to infinity. So it's basically everything but the number 2. Let's create a table of values for g of x. So we're going to plug in our x values, and then we're going to subtract 3. And then we're going to square that value. And finally, subtract 1 from that. And that last column will give us our y values. And the easiest numbers to fill in here are the numbers and their squares. So, for instance, negative 3 and 9, negative 2 and 4, negative 1 and 1, 0 and 0, 1 and 1, 2 and 4, 3 and 9. If we have x minus 3, we can find x by adding 3. And for our last column, we can subtract 1. We have a couple of y values here that are not going to appear on the grid that we have. And then we have also one other issue, and that is an x value of 2 is not allowed, so we actually have a y value that is undefined right here. So we're not going to get a y value when x is equal to 2 because x is not allowed to be equal to 2. So when we graph this, we have the point 1, 3. We would have 2, 0, but the graph will not have a point there, so I'm going to draw an open circle there. And then 3, negative 1, 4, 0, 5, 3. And so this gives us a pretty good idea of what this parabola looks like. But it's a parabola with a missing point, which we'll denote with an open circle. In C, we have a linear function, and again, no implied domain, but we have a very specific domain that is given to us. When we write that domain in interval notation, that is the interval from -4 to +2, and a closed interval since those values are included in the domain. We can create a table of values for this, our x values, and if we want to do two operations at once, just the y values are 1/2 times x plus 2. Now our x values need to range from -4 to 2. Since we're going to multiply those x values by 1/2, I'm going to choose to use even values only in my table. So from -4 to 2, and take 1/2 of -4 and add 2, and that's equal to 0. 1/2 of -2 is -1 plus 2 is +1. 1/2 of 0 is 0 plus 2 is 2, and 1/2 of 2 is 1 plus 2 is 3. So now we have our points which are -4, 0, -2, 1, 0, 2, and 2, 3. And the only points that should be graphed are the x values that range from -4 to 2, not beyond that. So this graph will only be a line segment. In D, we have another linear function, and so for this one, our explicit domain is x is greater than or equal to -1. In interval notation, this is the interval from -1 to infinity, inclusive at -1. And so if I create a table of values for this graph as well, x and our y values are 1 minus 2x. I think we can do both of those operations at once. And I need to make sure that my x values start at -1 and get greater. So 0, 1, 2, 3, etc. So 1 minus 2 times -1 is 3. 1 minus 2 times 0 is 1. 1 minus 2 times 1 is -1. 1 minus 2 times 2 is -3, and 1 minus 2 times 3 is -5. And I'm going to draw a dot, dot, dot here because x goes beyond 3. We're just not going to include all those values in our table. So our end point of the graph is when x is equal to -1, and that's the point -1, 3. And then we have 0, 1, 1, -1, 2, -3, 3, -5, and that graph goes from x equals -1 on the left and continues infinitely to the right. In example 2, we can also create a table of values. We have an implied domain here, though, because there is a division, and we know that the denominator in a division may not equal 0, so that means that x may not equal 1. Now let's create a table of values. So our x values, and then our y values are 3x minus 3 divided by x minus 1. So we can use any x value but 1. So for instance, let's use 0, 1. We'll use that one, but we'll see that the value is undefined. 2, 3, 4, etc. We're just going to use a sampling of values. If we replace x with 0, 3 times 0 minus 3 is negative 3, and 0 minus 1 is negative 1, and that result gives us a y value of 3. If we use x equal to 1, 3 times 1 minus 3 is 0, and 1 minus 1 is 0, and that is undefined. That's why we can't have x equal to 1. And when we replace x with 2, then we get 3 times 2 minus 3 is 3, and 2 minus 1 is 1. 3 divided by 1 is 3. Let's use 3. 3 times 3 minus 3 is 6. 3 minus 1 is 2. 6 divided by 2 is 3. And guess what's going to happen when we use 4? We're going to get 9 divided by 3, which is equal to 3. So it appears that our y values are always 3, except for when x is equal to 1. So x equals 0, y is 3, x equals 1. We don't have a point there, but in all other instances, the y value is equal to 3, so what we really have here is a horizontal line with a hole in it. This is what we call a removable discontinuity. Let's examine another function, h of x equals x squared minus 4 divided by x plus 2. The implied domain here is that x plus 2 may not equal 0, so x may not equal negative 2. Given an interval notation, which we forgot to do on the last question, in interval notation this is the interval from negative infinity. It didn't say to give the domain, so we're going to skip that. Alright, so we're just going to create our table of values for b here, and we're just going to exclude x equals negative 2. Or we can include it and just observe that we'll get an undefined y value. So I'm going to use some other values here. So let's use 0, 1, 2, 3, and let's see what we get. When we replace x with 0, we get a numerator of negative 4 and a denominator of 2, which gives us negative 2. When we replace x with 1, 1 squared minus 4 is negative 3, 1 plus 2 is 3, and that gives us a y value of negative 1. When we replace x with 2, 2 squared minus 4 is 0, 2 plus 2 is 4, 0 divided by 4 is 0, and we replace x with 3, 3 squared minus 4 is 5, and 3 plus 2 is 5, and so we get a y value of 1. So when x is 0, the y value is negative 2. When x is 1, the y value is negative 1. When x is 2, the y value is 0. When x is 3, the y value is 1. It appears that we have a straight line here. So I would continue this line infinitely in both directions, with one exception, and that is when x is equal to negative 2 on that line, we're going to have an open circle there because that point will not be included. So what we're going to do here is, in C, it's asking us to use the graphs of each function to write equations for the function in a simpler form with explicitly stated domains. So let's back up to A. A's graph is a constant function, and so we can rewrite it as g of x, or y, is equal to 3, and we can just say for x not equal to 1, because that accounts for the hole in the graph. Let's take a look at B, and for B, this looks like a linear graph with a slope of 1 and a y-intercept of negative 2. So this looks like it could be written as h of x is equal to x minus 2 for x not equal to negative 2. And there is a nice technique that we can use to make this graphing easier. That graph with a missing point is said to have what we call a removable discontinuity. And that's often called, more informally, a hole in the graph. And that missing point can be graphed with an open circle. Some rational functions have numerators and denominators which have a common factor, which can allow for us to remove that discontinuity algebraically. So in example 3, we're going to use that technique. And so what we're going to do here is we're going to factor that numerator, that's x minus 2 times x plus 1 divided by x plus 1. And we're going to cancel that common factor, but in doing so, we're canceling a division, so we have to be careful that we're not dividing by 0. So when we rewrite our function can be rewritten as f of x is equal to x minus 2 for x not equal to negative 1, because negative 1 would cause the denominator of the original function to equal 0, so we want to make sure that we have an equivalent. So now, in order to graph this function, we can just graph the line y equals x minus 2, which has a y-intercept of negative 2 and a slope of 1. But we can go to where x would equal negative 1 and insert a hole in the graph. In b, we can take and factor the numerator, common factor of x, and then cancel the common factors in our numerator and denominator, and be careful that when we rewrite our function can be rewritten as g of x is equal to 2x plus 1 for x not equal to 0, because x equal to 0 would cause our denominator of the original function to equal 0. So we're just going to graph the linear function with a y-intercept of 1 and a slope of 2. But I'm going to go back to my graph, and I'm going to take out the point where x is equal to 0 and instead insert a hole. So this graph will actually have no y-intercept. In C, we can factor x minus 2 times x minus 1 divided by x minus 2. When we cancel our common factors, this will give us h of x is equal to x minus 1, but we have to now explicitly state that the original denominator could not equal 0. If x minus 2 is equal to 0, x is 2, so we're going to state that that's for x not equal to 2. So I'm going to graph a function with a y-intercept of negative 1 and a slope of 1. But when I get to the place where x is equal to 2, I'm going to put an open circle or a hole or removable discontinuity in the graph. In example 4, we're asked to write these functions in simplified form with an explicitly stated domain. In other words, we're going to factor and cancel like we did in some previous examples here, but we're not going to graph them. We're just going to rewrite that as a function with an explicitly stated domain in simplified form. So what we have in A here is a complex fraction, and in order to simplify a complex fraction, we can take the two mini denominators and multiply both the numerator and the denominator of the big fraction by the least common denominator of those two, which are 3x. So we're going to multiply the entire fraction by 3x over 3x, which is essentially 1. So in doing that, as I distribute to each of the terms in the numerator, the first term in the numerator of f of x is 3, and the second term is x, so 3 minus x. And then in the denominator, I'm not going to multiply because we are going to have some canceling that can be done. 3 minus x is the same thing as negative 1 times x minus 3 because they are opposites. So when I cancel my common factors, I'm going to rewrite my function as f of x is equal to negative 1 over 3x, but now we have to acknowledge that we changed the domain by removing the denominator of 3x. So I'm going to say 4x not equal to 3. It's important to realize here that we also have another implied domain that x cannot equal 0 when we simplify this to f of x equals negative 1 over 3x. So there's an implied domain and then there's one that has to be explicitly stated. It wouldn't be wrong to state for x not equal to 0 and for x not equal to 3. Your turn to try. Pause the video while you try B. Your simplified form for this one should be g of x is equal to 1 divided by 15x for x not equal to negative 5. And again, it wouldn't be wrong to say and also for x not equal to 0. Here we have another complication, right? Because our denominator is 3x plus 15, but we need to realize that that can be factored into 3 times x plus 5, which will allow for canceling that common factor of x plus 5. In C, we have a couple of implied domains here. X can't equal 49 since our denominator can't equal 0, and also x has to be greater than 0 since that x is under an even root. But what we can do here is we can multiply the top and bottom of this by the conjugate of what's in the numerator. So the square root of x plus 7 and the square root of x plus 7. And then when we multiply the numerators together, that's a minus b times a plus b, which is always a squared minus b squared. So that's x minus 49 when we multiply those two binomials together. In the denominator, we have a factor of x minus 49, which we are going to cancel out. And so I'll leave it in factored form. Cancel common factors. That leaves us with a 1 in the numerator. So that means that h of x is equal to 1 over the square root of x plus 7 for x not equal to 49. And again, we have an implied domain here that x has to be greater than 0 as well, so it wouldn't be wrong to explicitly state that. By the way, at this point, it is okay to leave a radical in the denominator. It's your turn to try D. F of x equals the square root of x squared plus 5 divided minus 3 divided by x minus 2. Pause the video while you do this. Here's the final result for that last try this. X plus 2 divided by the square root of x squared plus 5 plus 3 for x not equal to 2. So in order to find this, we need to multiply top and bottom by the conjugate of the top. And in doing so, we get x squared plus 5 minus 9 on the top of the fraction. We're going to leave the bottom in factored form. And then x squared plus 5 minus 9 is x squared minus 4, which is difference of squares. That will factor to x plus 2 times x minus 2, and our x minus 2 factors will cancel. Interesting side note, the domain of the expression that results, aside from the explicitly stated domain of x not equal to 2, is all real numbers, because x squared plus 5 is a value or an expression that is always positive for every real x value.